Hello, my name is Rafał Furmański.
And I'm Piotr Golhawa.
We work at Opera Software, the best browser company in the world.
And today we'll be speaking about how we've managed to synchronize tens of millions of browsers while sleeping well at night. So we'll tell you a little bit about Opera and our use case for Scylla. Besides that, we'll tell you about the Cassandra, which was our first choice. But later on, we migrated to Scylla, and we'll tell you about the migration process and the results that we've got from the migration. And last but not least, we'll tell you about the two tools that we have developed in-house and open sourced. OK, so at Opera, we are creating browsers. We've got 350 million monthly active users right now. Opera was founded in 1995 in Norway, with headquarters in Oslo. We've got branches in several countries, like in Poland, Sweden, and China. Opera is a public company listed on NASDAQ, and we are mainly creating browsers. So there are two editions for desktop browser, Opera for desktop and Opera for gamers. And there are also four main products for mobile, like Opera Mini, Opera for Android, Opera Touch, and Opera News. Opera is a pioneer of many concepts that we find prevalent in modern browsers, and we are continuing to introduce unique features to our products, like, for example, built-in VPN, built-in ad blocker, and integration with chats, most popular chats, so that users can share the content from the web seamlessly with their friends. We are using Scylla to synchronize those browsers, the desktop browsers and mobile ones. Basically, we sync every object that is generated during the use of the browser, like favorite sites on speed dials, bookmarks, open tabs from all devices, browsing history, passwords, and browser preferences. An architectural overview, so you've got the general idea what we are talking about. We've got user that is logged in to the auth opera.com, which is our central authentication server. And later on, when the user changes the bookmark, for example, the request from the browser is directed to the nearest data center. The request is processed by the backend servers and finally saved to the database. If it was a commit change, like something changed on the bookmark, for example, we send notifications to other instances of the browsers via Firebase cloud messaging. As on the infrastructure part, we've got two data centers, one in US, one in Amsterdam. There are 10 backend servers with Python+Django applications, backend applications, and 13 Scylla nodes in each of the data centers. The rest is not that important. As for the schema, we keep a table for each object that will be synchronized between the browsers. Like in this example, we have a bookmark. The user ID is a partition key so that the user data is collocated, and then we've got other two which comprise the primary key, its version and ID of the object. The version is a clustering key in our case, so that we can make queries like this. So, for example, get all bookmarks for user Adam from version X. And the second type are change, remove, add bookmark requests with certain version and object ID. And now Rafa will take you with our migration from Cassandra to Scylla.
Thank you. OK, so we started with Cassandra since version 2.1, and we immediately got hit by some very, very ugly bugs, like lost writes or ghost entries showing here and there, null pointer exceptions, out-of-memory errors, crashes during the repair. It was really a nightmare for us. And besides all of these bugs, we observed very, very high latencies, read and write latencies. On average, everything was quite OK, but P99 read latency could be like 5 seconds. So besides that, very, very long GC pauses. Basically, the longer node was up, the longer the pauses. And stop the world compactions basically caused that our gossip and binary protocols, when you run node to status gossip or node to status binary, it shows not running, even if node to status is telling you that the node is OK. Besides that, very insane CPU usage. Our nodes have 24 cores each, and we observed a load like 50 or 70, even 70 on each of these nodes. Also, the crashes, restarts without specific reasons, and problems with bootstrapping the new nodes. When you bootstrap a new node, it has to stream data from the other nodes. And if one of these nodes is down because of all of these problems I mentioned before, you basically had to start over the bootstrap process. So, yeah. And our solutions to these problems was to add more and more Cassandra nodes. We observed that in a minute that node reaches 700 gigs of data, the disk usage, it became unresponsive. We also try to tune every piece of Java and Cassandra configs. And if you come from Cassandra world, you know that there's a lot of things to configure there. I also try to seek help from Cassandra gurus, but all they can say to me was, I never see something like this before. So, nice. We even done something really, really bad. I'm not proud of it. But we introduced a cron job to restart Cassandra nodes periodically because of all of these problems. And it helped a bit, surprisingly. OK, our journey with Scylla began in 2015, in September, on Cassandra Summit. I saw there Doors and Avi's presentation about the new shiny database called Scylla. And I was really amazed about its shard per core architecture and future plans, and also that it was written in C++, not in Java. So basically, I started to observe the development process from this time. And it wasn't production ready yet, of course, in 2015. But in July 2018, I believe counter support was added to the Scylla. So I decided to create a first cluster of Scylla and perform some benchmarks. Immediately after this, I decided to migrate all our users' data from Cassandra to Scylla. And I'm happy to say that in May this year, we removed the last Cassandra node from our production cluster. Thank you. As for benchmark, I prepared 3 bare metal nodes, exactly the same nodes as we use on production. We use, of course, Cassandra Stress with mixed workload, 1 table, bookmark, and production key space sync, set up the same exact way as in production. And as for results, we get almost 3 times more operations per second, and our latency was about 10 times less in Scylla. And what I can say is that in case of Scylla, I was throttled by our 1 gig networking card, so these results could be even better. OK, now I will describe our migration process, because it wasn't like migration processes described here using SSTable loader or Spark, we decided to migrate from our application. So yeah, our backend uses Python and Django framework. So we created our in-house library for connecting Cassandra or Scylla with Django. It's called Django Cassandra Engine. And I had to add support for multiple databases to this library as a first step. The second step was to prepare a 3-node cluster, basically, per DC. Of course, with monitoring, because monitoring is the most important thing you need to do. And then I updated my backend to be connection aware, so I could run those queries using the using clause from my application. Then I moved a few test users to Scylla, basically me and my coworkers, so I could observe for a while if it works okay, if no errors are there. And as for next step, I moved all new users to Scylla. We have around 8,000 new users daily, so yeah. And then I then I started slowly to migrate my data from Cassandra to Scylla, decommissioning nodes from Cassandra and adding them to Scylla cluster. The next step was to disconnect Cassandra and basically did some cleanup, and that's all. This is how databases dictionary looks in Django. Our production setup is connected to both Cassandra and Scylla databases at the same time, and we can run queries against Cassandra or Scylla every time we need, basically. Okay, when request comes from the client to our backend server, we need to determine where user data is located. It can be either in Cassandra or in Scylla. So we use cache for this. We have memcached cluster, so the first step we try to get user connection from cache. And if it is in cache, then we can safely return the user store. User store is a column that holds information about our users. And if cache is empty, then we try to get user store from Cassandra, and if it fails, in Scylla. And as the last step is to just update the connection cache. So next query will be served from cache. Okay, we had some requirements to our migration script. The first and most important one was the ability to move users' data from Cassandra to Scylla and backwards in case of any problems. Also, it has to have the consistency check after migrating. So basically, we compared every piece of data and check if it matches, basically. And of course, concurrent execution is a must, so we could run multiple migration scripts in parallel. And we had to, of course, measure everything: number of migrated users, migration time with distribution, errors, of course, with reasons, and failed migrations. As for algorithm, it's pretty simple. We pick a free user to migration. We use Redis for this, for atomacy. And we added one column to the user store table. It's called migration pending. It basically cuts off user from sync if it's set to true. Migration takes usually 2 seconds, so it's almost not needed, but yeah, also clients have built-in backup mechanism, so if one request fails, the browser will retry this request in the future. So it's not a problem here. Then we copy all the data to ScyllaDB, perform consistency check, and remove leftovers from Cassandra, and also update to the connection cache. And as the last step, we set migration pending to false. There were, of course, some challenges during the migration. Most of them were related to the Cassandra. We had lots of timeouts and unavailables. Even if we have like 3 nodes left in Cassandra and not many users, there were still timeouts and unavailables. So it wasn't that easy. Also, migrating huge accounts could take some time. 2 hours, I guess, was the biggest account to migrate. And also, of course, user is cut off from sync during the migration period, but as I told you before, it's not a big problem because usually migration takes like 2 seconds. And of course, synchronization of concurrent processes, but it was done by using Redis, basically. And here are our results. We were able to reduce our number of nodes from 32 a year ago to 26 right now. And we have plans to even further reductions. We just need to put 10 gigs of networking to every node and maybe buy some brand new shiny NVMe drives. I think 8 or 10 is possible. Also, we have faster node bootstrap time. Now it takes like 2 hours to bootstrap a new node, which is OK. Previously, it was days. And we have huge drops in latency. We had to use logarithmic scale on the last chart to show this data. So previously, P99 read latency was 5 seconds in Cassandra. Now it's 4 milliseconds. And the most important thing, no more sleepless nights for our on-call engineers. Back to you, Piotr.
OK, so last but not least, we've created 2 tools to deal with Scylla open source. The first one is Scylla CLI. This is a console script mainly used for checking the status of the cluster and performing range repairs. It connects to Scylla API via SSH tunnel. It is written in Python, and you can easily install it via pip. Why do we have created Scylla CLI? As I can remember, the node tool put stress on our nodes when trying to do the repairs, and that was unacceptable for us. And we chose to work with Scylla open source for now, so we needed a tool that would do repairs and do not put stress on our clusters. It performs repairs only on the primary range on the Scylla node. It performs advanced repair techniques like sub-range repair, so we can take only a sub-range on the node, not the whole node. It performs scheduled repairs, so what to repair and when. It has a built-in retry mechanism, so if something goes wrong, then it tries to retry the operation. It has real-time progress and ETA. And it is really easy to use, as you can see. And the second tool it uses shard awareness feature, which is a Cassandra native protocol extension. We are inspired by a talk on last Scylla summit by Piotr Jastrzębski. He achieved over 2 times latency decrease, so we figured that maybe we can have this as well and have some performance gains. But there were obstacles, because there is no Python driver support, and even if there was, we would need to create many connections from our backend servers to the Scylla shards. We did the math, and it would be almost 200,000 connections from one backend server. So we came up with a solution. We created a GoSQL proxy, which is a proxy running on the backend server, which proxies the request to the Scylla shards. And using this solution, we need to create only 900 connections from one backend node. Yeah, so like I said, we are using shard-unaware Cassandra Python driver from data stacks. And all requests are proxied through GoSQL proxy running locally on the node and then further to the Scylla cluster. So we wanted to write as few lines of code as possible when creating this piece of software. So we've created an addition. Basically, if we wanted to, we needed to parse every message type in Go, which is kind of troublesome. So we came up with a solution that we will create one additional type of message, and it will be a message itself, encapsulated with the routing key for shards, and this resulted only in few lines of code, very few lines of code in GoSQL proxy. So our results. Of course, reduced number of connections. We ran it in production for a few days. Everything is working okay and stable. And here you can see the results before and when we turn on and turn off and turn on the shard awareness on the proxy itself. And we can see that we've got gains on the average request, like 70%, but the biggest gains are on P99. And the takeaways. Go download the Opera browser, give it a shot. We've created our Django Cassandra engine library, so you have a Cassandra driver to use with Django framework. Go give a shot to the Scylla if you are using Scylla open source, and of course, if your problem is number of connections, then go and try the Scylla proxy. And that's all. Thank you.